Hello viewers, and welcome to a new STM32 World video. In this video I am going to teach you everything you need to know about SD cards and FatFS. This video was actually made on request by a viewer of one of the other videos, and I thought that was a good idea. So let's crack on with it. As usual, I have actually created a page on the STM32 World website wiki, which is called STM32 SD card with FatFS, and let's click on that. And these are the SD cards that I'll be using in these videos. There will probably be two videos, but let me explain a bit later why that is. SD cards can actually run in two different modes. You can use SD, it's a native interface, which have 4 data line, data 0, 1, 2, and 3, or they can run in SPI mode, where you only have the usual data in MOSI and ISO. So two different modes that SD cards can run in. Today we are going to look at the native interface that is called SDIO. Now, SDIO is not supported on all STM32 microcontrollers, but it is supported on the STM32F405 and a lot of others. I think most of the 4 series will have SDIO. SDIO is a peripheral that takes care of a lot of the the translation to speak with the SD card, the protocol with the SD card. So it is a bit simpler. So we are going to start with this. But of course, to use SDIO, you will need it wired up correctly, and you will need probably a PCB with a breakout board or something like that. I am going to use a board I had lying around. I can't actually show you a video, and I can't show you the full board because this is actually a customer project, but it is mostly identical to my usual STM32 World MCU board, with one different, and that is that it's got the SDIO card I have shown here, how it's wired up, and it also have the LED. It does have a LED, but that is wired up to I think it's PA4. You can see it will show that up there. Doesn't matter. But apart from that, it's identical. It's using a 16 megahertz crystal, and everything is like it usually is. So as usual, I have created a standard project where I have configured the clock circuit, and I have configured the LED port up here, and I have configured the SVD pins and a UART pin. And if we look at the actual file, I redirect the printf to the UART, and I am printing out a tick every second. So let's try to run this. And here we have the output. There we go. So the loop and the tick kicks up, and it counts how many times it goes through the loop for each second. So without further ado, let's try to enable the SD card again. We have the schematics here. I have the SD card inserted. It is hooked up to the SDIO. First step is to go down under connectivity, and you will have the SDIO here. Now, SDIO can run in multiple modes. It can run in a 1-bit mode and a 4-bit mode. For some bizarre reason, I don't know if it's a bug in the SD libraries or the bug in the actual peripheral, but if you enable 4-bit mode straight away, it will not work because because it only supports, I think SD cards only support 1-bit communication initially, and they have to be told to switch to 4-bit mode. So for now, we will enable a 1-bit. So here we have SDIO. We run it full speed, no divider, and that means it will actually run probably at 84 megahertz or something like that. We see the pins defined here. There's no pull-up. Now, SDIO require a pull-up on every pin except the clock pin. On this board, I actually have them, but if we did not have them, we could enable the internal pull-up, and for short traces that would probably work just fine. But in this case, we do have the pull-up, so we don't need to enable those separately. So that is pretty much all we need to do with the SDIO to make that run. Now, having an SD card without any file system on it is a little bit, it's a bit tricky to be useful. So let's go down here under the middleware, where you will find FatFS. And since we have already enabled the SDIO, SD card is natively supported by this. You will see that we get a warning over here in platform settings, and that is because we need a GPIO to detect whether the SD card is inserted or not. If we look again in my schematics, we have an SD detect pin, and well, we could use we can use PA15 for that. That is the one it is wired up to. So we will make this a GPIO input. And then down here, we will use the PA15 as the detect pin. So that is pretty much all that needs to be done there. Now, we have an error over here. The clock is because we enabled another, so we will need to recalculate this, and so now we are running back at 168. We need that 48. So the SDIO is actually, I think I said 84 before, but it is actually running at 48. I think it's running off this 48 megahertz clock down here, which is the same that is being used for USB, actually, if we enabled USB. We need to configure some of the FAT settings. There is a lot of configuration in the FatFS. One thing I know we need to enable is ExFAT, and ExFAT can only be enabled if we support long file names. Now we can enable the ExFAT. Let's go through the settings briefly, and I don't want it to be read-only. I want to be able to write this, but let's enable pretty much everything that makes sense. It's using Latin 1, that is okay. We only need to support one volume. If you have more than one partition, you can enable multiple volumes at the same time. We don't want to bother with that. If you're actually using this with FreeRTOS, you need to make it re-entrant, but we don't need any of this stuff here. Advanced settings, we leave that as it is. So this should pretty much be all we need. We have configured the GPIO. So, well, okay, one more thing, and I think it is a bug in my PCB design actually, but the GPIO that we used for the detect, actually let's give it a name. We call it SD-DET. SD detect is actually active low, so if it's high, there's no SD card. If it's pulled low, but for some reason it actually doesn't work very well. But if I on my PCB, but if I pull it down here, then it'll work, because it will always think there's an SD card, even if there isn't. So anyway, let's generate this code. And let's look at what it is actually generating. So if we go down to our main function, you will see that it now initializes the SD card, and then it initializes the FatFS on top of that. And the most interesting function is down here, where you can see it initializes the SDIO instance, but it set it to a 1-bit wide bus for now. If we changed it to 4-bit, this would be 4-bit, and we would have to do an extra step here to initialize this SD card in 1-bit mode first, and then go up to 4-bit. I will get back to that a bit later. But that is the initial. So let's see if we can actually get some information. And as usual, I have cheated a little bit and did this already. So let's look at the after the initialization. So let's get whatever SD card information we actually have. We can get the SD card block size, and if it's initialized correctly, this should print out. So let's try to run it with that here. And that didn't work. Why doesn't that work? Detect SDIO. I think it might actually be you have to initialize this separately. So let's I did in my other code. Let's see if that helps. Down here under my user code 2, I will initialize the SD separately. Let's try to run that and see if that works. It worked. So basically the block size is 512, and it got 121,000. If you calculate this, it becomes about 60 gig, which is the card that we are using. So it all adds up. So actually, since I can't be bothered with this to make 2, let's switch this over to 4-bit straight away, because it is obviously needed anyway. So if we generate the code, I might as well show you that straight away. What happens is you need to initialize this in 1-bit mode, the SD card, and then you can switch it over to 4-bit mode like that. So you config the white bus operation, and I'm sure if you dig into this code, you will see that it is doing some communication with the card to let it know that we are now running in 4-bit mode. I'm not going to dig into this in detail, but now we have enabled the 4-bit mode. So let's try to run this and verify that we can indeed communicate with the SD card. Now let's look at FAT. FAT has already been configured. I am going to show you a little hack if you have problem with the detect pin. What you will find in the libraries is that there is a weak function that that returns, and we can override that weak function as usual. Up here in our code, we can override that BSP SD is detected, and if it returns SD present, it will be detected. So if we do like that, it will always think that there is an SD card, even if there isn't an SD card. So that is a start. Let's do that. So using the FatFS, the first thing we need to do is to mount it. And there is a standard way of doing that, and let me take the code for that. Will look something like that. We are using fmount. Now these variables, which is the SDFatFS and the SD path, each mount point will have a FatFS on it, and it will have a path to that logical drive path. Now, if you think back to Windows and DOS before that, you have drive designators, you have A, B, C, D, E, F, whatever. On STM32 with FAT, these will be numbered instead. So you will have a 0 colon, 1 colon, and so on and so forth. But if we just leave this empty, and I do believe it is a global variable, so it will contain all zeros. It will be an empty string by default. If we set this to it will pick the first FAT partition that it comes across on this drive, on the SD card. Now each of these FAT commands will return a, let's look at the command, the declaration here. It will return an F result. An F result can be okay, it can be disk error, it can be not ready, no file, no path, etc, etc, etc. Usually we're just interested in if it succeeds or not. So in this case, we will say if it's different than FR OK, we will print an error, and then we'll go straight into the error handler. There is no point in continuing. So what to demonstrate an interesting thing here, let's in this device keep track of the total uptime. How long has this device been running forever through reboot, and keep this variable. So up here in a private variable, let's do a 32-bit total uptime. Now, since this is a global variable, it will be initialized to 0. So let's create a file, and for this information, after we mounted this, no, we also need a file name for this file. We can define this as a constant, so that it is just stored in the flash memory. So where are our private variables here? So let's do a total uptime file name and call it uptime dat. This will create a file. This, yeah, well, okay, and we go back to this. So if we want this to survive, we cannot just create it every single time. We will need to check whether it exists. So I came up with a bit of code here, which I will show you. And at that, I'm not going to develop it step by step, but here, what I'm going to do here is I'm going to try to open this. I store a file. This is already defined. We could create another variable, call it the total uptime, and I will open an existing file. That means I'll open the file if it exists, and then I will read the uptime for that file. I'll just read the 4-byte of the uptime, the total uptime, into a total up, and I'll print out the total uptime. Then I'll close the file again. If I can't read, I'll print an error. If it does not exist up here, if it cannot open that, then the file did not exist. Let's create it. So we do an fopen again, but this time we do an fa create always. That means the file will be created no matter what. Now, if we did this anyway, I mean, it would overwrite whatever file was there. Then we write a 0, the 0, it will be at that time, into the file, and we will say we created it and close it. And if it fails to write, we will complain about that. If it fails to create, we'll complain about that. Now let's try to run this and see if there was an error. Oh yeah, we don't have these, so we need to define that somewhere. We can do it here actually. UN32T V bytes and R bytes. We'll use these variables. They return how much was written or how much was read. Let's see if that builds. It builds. So let's try to run it. Now I have played with this SD card before, so I would expect it actually have a total uptime of 66,844 seconds. So now we have this file and we can read it. We can read data from it. So the next step will be down in our tick handler down here to play with that file. And where are we? We're here. So every time this run, every time we get into this tick down this one, which we do every second, let's increase the total uptime, which is that variable we just read from the file, and then we will update that total uptime file. So we do that after. Let's print the tick first. So we'll open the file. Now, we know at this point it should exist. It could still fail, so it'll go down there. We don't call the error handle in this case, we could. But we open this file for writing. We write the total uptime down in it and check that we could write it. Let's try to build this and run. So 66,400. Let's actually hang on. Let's print it out while we're at it. Total equals. It's also a loop. Let's print it out. So now you'll see it counts up from 66,500 just for the hell of it, because we started this new project. Let's after we initialize it, we read this value. I'm not going to change the code, but I'm going to make a temporary hack here and say total uptime equals 0. That means it will actually start with 0 from we started developing this project. There we go, and 1, 2, 3, 4. We remove this line again. So now we are keeping track, and the interesting part here is that every time we reset this, let's find the other here, we can actually, if we probe STM32, it will reset the MCU, so we can try to reset, and we can see the counter. I didn't flash after I need to flash that. It starts at 10 now. It's 14, 15, 16. Now, if we reset at 25 or 5. there, it reads 25 and it continues 26, 27, 28. So now, no matter how we reset this, let me do the hardware reset. I have a button on the board to do that. Let me do a hardware reset there. And you can see, so every second, a new total uptime in seconds is written down to this file, and it is stored on the SD card forever. Now, how do you check? Let's play with that. So how do you check what files? How do you read file information? Let's create a function up here. And I again have cheated a bit. Where is it? I have it here. Like a directory function, or ls if you are a Unix user. So let's do the ls. So how do you do that? Well, you open a directory. It's got a command from that. Path is, well, will be empty. And then you read, then it will read the root directory, and then you continue until it fails. So you basically keep reading that directory until it does not return FR OK. If it's different than FR OK, then we break and go out of this. And apart from that, we'll print it out. We will also down here get the number of free, how much free storage are there. There is a command for that called get free, and it will update some variables in the FatFS pointer, which is the number of, and it will return the free clusters. So let's try to run this and see if we can make, no, we need to actually show it. So down here, we could say, we could create a, no, actually let's start by showing it after we initialized all this stuff. We could do it here, call ls. I want to make this one, I don't want it, oh well, it's okay, let's just run it and see what happens. There we go. I am going to stop this. So we'll see there is some files on this. There's the uptime that we're using. There's one called ticktext and bigdat. And there's some files I created just to use some space on this board. And you can see it's a 60 gigabyte card, and we have used about 10 gigabyte of data. These are, strangely enough, 1 gigabyte each to make that easy. So we have a bunch of files here. We have a folder dive here, a directory called lost plus found. I have obviously, this is a Linux thing. It will create that if it has a, you run a file check and it is not complete. I have never deleted that, but at the moment we are only using this uptime dat file. Rather than showing this, let's actually do it periodically. So let's create a here, where are we here? Let's do a next ls, and this one we will run every 10 seconds. And let's go down to our here. We will also open a file if it exists. So it will complain about that, but I'll do that file later. So let's try to run. What is it complaining? We need a big file name. I think that was all it complained. It's complaining about something else. Oh, it needs a buffer. We can, where did I define that? Is that a global variable? I'm going to define a couple of other files, file names. Let's do that up here. We are going to have a big file where just to see how fast I can read data, and we are going to put our tick lines into a file as well every time we print them. I will need a buffer. Oh, yes. So let's start with the big file actually. Okay, here. Trying to memorize what I was doing. Okay, I got it. So when we start up, rather than printing out the ls, where are we? We are here. What I want to do is I want to create one more file. So I am going to create a buffer of 1K in memory. I am going to initialize that 1K buffer, just 1, 2, 3, 4, 5, etc. And then I am going to store the UV tech so I can time this. I am going to open the big file name. I always create a new one, and I write that into 1024 times, which essentially means that this will be a 1 megabyte file. We write that into this file if you look, and then we print out how long did it actually take to write this file. Let's see if that works. It compiles, and let's see what happens here. It complained. Okay, let me kill this stuff down here by not updating the now variable. And let's see what actually happens. Okay, now it actually worked. So writing a 1 megabyte file in this case took us 580 milliseconds. I actually think it will work now. Let's try to run. So down when we are doing our LSF at 10 seconds, I'll open that big file and I'll read it from end to end, and then how long did it take to read this file? I'll then print the ls and then move on from there. Let's try to run that. Not sure why it failed before. Let's see. Now it runs. No errors. It took 580 milliseconds to write this file, and here when we are reading 1 megabyte took 230 milliseconds. I want to show you a little detail here, which is interesting. Now, remember when we were initializing SDIO, we were using a 4-bit white bus, but when we initialized it down here, we initialize it in 1-bit mode, and then we switch it to 4-bit. Now, if we remove that, so we're running in 1-bit mode all the time. Let's try to run that here. It failed again. Oh, nope. Okay, that was not overly impressive. Maybe it has to be switched to 1-bit mode internally. What? Let me. Unable to write. doesn't seem to. I seem to remember. Wait, let me check. That it takes a little bit to settle. Let's see if it helps if we go up here. When we start, let's try to do starting. Let's do a hell. There's a wait 500 milliseconds before we start to do anything. Is there anything else in here I have overlooked? No, it should work. Oh. No, it will not. I'm going to take a short break and get back to this. I managed to figure this out. This is probably when I'm using STM32 CubeMX and the most common thing that I get wrong all the time is that I forget to enable the interrupt. So I didn't have the global interrupt for the SDIO enable, and after I enable that, everything clicked into place. So let's try to run this. And it runs. Let's try actually to do that demonstration I tried to do earlier by not switching this into 4-bit mode. And let me remove that delay I did up in the beginning, because I really don't think that's necessary. And let's try to run it in 1-bit mode. Let me get the error again. Let me try to. Not a very convincing demonstration, I must admit. I am quite sure that I had this working at some point before. Maybe we do need that delay. Oh, okay. I will probably get back to this in a future video. I need to figure out what is happening there. But you see, we read this file and it takes about 0.23 milliseconds, 230 milliseconds to read the 1 megabyte file. Let's do a little bit more. Let's write this tick file. You can see we already created this tick file. Did we actually do it? The file is there. But let's see if we actually create the file. Up when we start. Update file name. We need to create this tick file always. Let's see if we actually did that. No, we did not before the buffer, so we can do it here. Now, tick file is comment is wrong always. So we always create a new one of this tick file name, which we set to tick text. So the file will exist no matter what. And then we can do down in our main loop every time we do this tick and we print out, rather than printing it out directly, let's create a string. Where are we? We are here. When we tick this out, we update the uptime, but rather than printing, let's do it this way instead. We create a string buffer. we have this and we print it into this string, and then we print the string rather than printf directly out, and then let's dump this into the tick file on every single second. We will open that tick file and we will open it in append mode, and then we will write the string length. We will write this string down to this file. I actually think to make this work, it should be string line +1, because we need to print the strings of 0 null terminated, and we need to write that in as well. So I think this will be correct. So let's, there is an error. We called it loop CNT. There. Right, it takes 580 milliseconds. Now this loop will update the total count file and it will dump into the tick file. And you can see the tick file is now 380 byte. Next loop, it will be longer. Now it is 769. So now the tick file will keep growing, and it will grow until it runs out of space and there's an error. So that's pretty much all I wanted to write today. Well, let's see, there is a warning there. I don't. Oh, string length implicit, so I need to include the string library. Project built. There should be no warnings. No, there isn't. Let's run it again. So I am probably going to make a little follow-up video very soon to figure out why I could not run this in 1-bit mode, which should work. I mean, I don't see why it would not work if I comment that out. Let me try one more time. Nope. We set that to 1-bit. It should work. Anyway, I am going to I'm going to make another follow-up video on this when I figure it out. But meanwhile, this is pretty much all I wanted to say. I have showed you how to enable the SDIO. It can be a little fiddly sometimes, and get FatFS running. Once it's up and running and once everything is working, it usually works really, really well. And usually doesn't fail. It's right. So in the next video, I will follow up if I figured out that 1-bit versus 4-bit mode, and I will try in the next video to run this in SPI mode. And for the SPI mode, I will use a little adapter that I made myself out of one of those SD to micro SD adapters, and I just solder some jumper wires in it, and that should make it possible to run this in SPI mode. And on that, I will be using the STM32 World board, as I'm always using, and that's pretty much it. Well, I hope that it was a little messy, but I hope that you learned how to use an SD card on an STM32 microprocessor, unless you need to do it with SPI, in which case you will have to wait for the next video. As usual, please like and subscribe down below, and have a wonderful rest of the day. Earlier in this video, there was a bit of confusion between 1-bit mode on SDIO and 4-bit mode on SDIO, and I managed to figure out what is going on. Now, if we look at, you have to be clear about which mode you want to run in all the way. So if you go into STM32 CubeMX and set it to 1-bit mode, let's generate that code so that up here it is set to 1-bit. We don't need this one. We initialize the SD card and we don't switch to 4-bit mode. If we try to run this, it will run perfectly, and let's look at the performance here. So it took 850 milliseconds to write that 1 megabyte file, almost a second to write a 1 megabyte file, and we can read it in 500 milliseconds. Now, if we switch to 4-bit mode in here, so we can do like that, generate code, then we need a little bit of extra doing in the setup, and I would actually consider this a bug in STM32's HAL libraries. If we set this to 4-bit here, it will not initialize the SD card. We have to initialize it as 1-bit there, and then we need to switch it to 4-bit mode there by setting the 4-bit SDIO bus wide 4-bit. If we do that and try to build this, I was building. Okay, let's run it. We'll see over here, it is still working. Now it only takes 500, so it shaves up almost 300 milliseconds for writing, and reading 237. So it becomes significantly, not 4 times faster, but not even double the speed, but it becomes faster. And I think we might be at I don't know if we're at the limit of the SD card, since writing is slower than reading. I'm not sure about that, but that works. Another thing I figured out, which is interesting, if we leave this as is, go back in here. Did I want to do here? No, okay, we can go over here. I noticed that if you don't initialize, I think I had that error as well. If you don't initialize the SD card here, let's try that in 1-bit mode, actually. So we go back to 1-bit mode. I think that's what I did earlier in the video. So let's generate code. Now, the interesting thing is, if we comment all this out and just do with what they generated and try to run that, you'll see that we get an error up in the beginning. It can't read, but the FatFS is still working. So if that was the error I saw earlier in the video. So this information is not being pulled in, it's not being initialized, but the FatFS must initialize that SDIO on its own. And I think, if I'm not mistaken, if you now run this in 4-bit mode, generate code, I'm not sure this will work, but let's try it. So if we try to run this, it will definitely fail up at the beginning there, and it can't create. So in other words, if you want to run in 4-bit mode, you need this piece to initialize the SD card, and you need to run that help config. I wonder if you can actually comment this out, if that will work. I haven't tried it. It will definitely still fail up at the beginning. And it still fails completely. So, in other words, in 1-bit mode, you can run it exactly using the code generated by STM32 cube MX. But if we want to run in 4-bit mode, we need to initialize the SD card first and then switch on the write operation afterwards. There, and then everything works. So it was just I managed to figure it out after this is a day after I created the rest of the video. So I will end this video a second time and hope that you will have a great rest of the day.